Okay, welcome to the first lesson on the chapter 4 of our module, which is devoted to the material point in one dimension, or the famous infinite dimensional Hilbert spaces. The plan of the chapter is very similar to the plan of the chapter on two-level systems. We are going to go first through the description of the system, and then later to the dynamics. The difference will be that in this case, the dynamics will take much longer, and there are many varied possibilities, much more varied than the one for the two-level system. So today, in this lesson, I'm going to speak about the description, the Hilbert space, and the states, the famous wave functions, and then the operators position and momentum. And the next lesson will be about the dynamics. First, something about the generic Hamiltonian, and then start studying some examples. As I said previously, and I will repeat again when we go to the dynamics, here we are in infinite dimension, therefore, in general, the Hamiltonian cannot be diagonalized exactly, and we're going to study a few cases where this exact diagonalization can actually be done. Okay, so let's start with the description of a material point in one dimension. So I will start with comparing the infinite dimension with the finite dimension. Right? So what is a state? Right? In finite dimension, we have written it something like this. Is a vector. Sometimes we can represent it as C1, CD. Right? Now, in infinite dimension, however, and this can be a basis of any physical quantity. Every basis is a good basis, can be a basis of every physical quantity, can be a basis of energy, can be a basis of spin, can be something else. Now, let's look at position for the moment as our basis, our physical quantity we look at. Position is a continuous variable. Therefore, I will not be able to label position by an index n that is countable. Instead, the state written in position will look like this. So with a function. So to a state, there corresponds a function. Of course, a vector is always a vector. That's why I have these objects here that I will describe later. But essentially, there is a correspondence. So if you want here, if I were to represent this thing, I cannot again do it as a vector. The analog of this representation would be, I put the x-axis and I draw my function on it. Of course, this can be a complex function, so I may need a complex axis. Okay? So this is the difference, the analog and the difference between finite and infinite dimensional system. Now, we had the normalization of the state. The normalization here for finite dimension was that sum over n Cn square is equal to 1. What is going to be there? Well, you can imagine integral dx psi x square is equal to 1. So now, and this function is the famous wave function. Okay, so that for historical reason, because Schrödinger derived an equation that formally is a wave equation, this object is called the wave function. Good. So there is a one-to-one correspondence, I repeat it again, between the state and the wave function. Now, this condition, of course, cannot be satisfied for all the functions. Right? You may say, well, which ones do not satisfy this condition? Well, imagine that a function is such that this is the case, right? Then I cannot find a constant such that if I multiply by the constant, this would become 1, right? Because this constant would be 1 over infinity. So in order to define the normalization, I must exclude, these are not valid functions. I must exclude the functions whose integral, by the way, sorry, here I should have specified the integral is over the whole real axis, so between minus infinity and infinity. I should exclude the function such that the integral is infinite. This integral square is infinite. And this leads to the definition of the Hilbert space. So the Hilbert space that we are going to use in infinite dimension, H for D infinity for quantum mechanics, is usually denoted like this, L2 of R, where the 2 represents the square, the R represents the fact that this X is a real number, and it is defined as the set of functions from the real to the complex such that integral psi x of square dx is smaller than infinity. If it's smaller than infinity, I can always later normalize and take those that are normalized correctly at 1. So these are called the square integrable functions. Okay, now you may ask, what is the scalar product between two vectors in this space? Let's again compare the finite and the infinite dimensional cases. I will write it here. So in the finite dimensional case, remember that if I have a basis, right, in this case a particular basis, and I have another vector phi that is represented by D, sorry, maybe not D, A1 to AD, then the scalar product psi phi will be the sum for n equal 1 to D of Cn star d a n. Okay? Well, again, here, if I have another function, phi, then the scalar product psi phi will be integral minus infinity to infinity dx. Psi is on this side, like here we have to take the complex conjugation, psi star of x, phi of x, dx. This is the scalar product for the square integrable functions. Again, I hope that you see the analogy between what we did for the finite dimensional case and what we are going to do for the infinite dimensional case. The structure is the same. Essentially, there are integrals to be taken instead of sums. Okay, at this point, however, I have to tell you that there is, among the things that are written here on the whiteboard, there is one object that is a bit bizarre. And we have to discuss that object. That object is this one. What is this x, this kind of vector that represents, obviously, a particle localized exactly at that position? So let's study it, and we are going to see that it's an object that has kind of unpleasant properties, but if it's used correctly, is not harmful. So what would be the state psi equal to, let's say, x0? Again, these would represent a particle that is exactly localized, exact localization at x equal x0. Okay? Now, you plug it in there, right? Let's try. X0 is equal to integral dx psi x of x0 x. Now, what is the wave function? Okay, what is the wave function that in this sum singles out x equal x0 and destroys all the others? Well, obviously the only possibility would be delta of x minus x0. So you would say that the wave function corresponding to a perfectly localized state is the delta function localized at that position. This looks absolutely reasonable, right? However, unfortunately, integral delta x minus x0 squared dx is equal to infinity. There are various ways of doing it. You can try to take any limit, any series of functions that converges to the delta function, like Gaussians, more and more narrow, or squares, and you can prove these. There is another argument. You could try to look at what this is. This is integral delta x minus x0 times delta x minus x0 dx. And you use this thing to evaluate this function in x equal x0. Right? So you look at this as a generic function. So this would give me delta of x0 minus x0. This is delta of 0, and this is infinity. Okay, that's just a proof of this statement. But what does it mean that the delta function, the square of the delta function is infinite, the integral? It is not a square integral function. So it does not belong to our Hilbert space. So this guy does not belong to L2 of R. So here we have a, what I would call before a kind of unpleasant situation. Unpleasant meaning that we are decomposing a vector that belongs, maybe I should write it, let me write it in a, I just write some of the things that are written there in a more compact way. Erase all these. So what I meant unpleasant is that usually we have a vector is equal to sum of vectors. But here we are writing psi is equal to sum psi of x, x. This is a vector that is valid. This is not a valid vector. So this notation is a little bit problematic from the mathematical point of view, but it can be used for practical purposes, and I can tell you essentially all physicists, but those who are really into foundations and into very serious mathematical problems, they use this notation. So this is not something I'm just introducing because we are not good enough. Everybody does that. For instance, these guys have a kind of interesting property. They look like a basis. Again, it's not a proper basis because these are not vectors, but they look like a basis in the sense that if you take x1, x0, what is this? Well, this is integral delta x minus x1, delta x minus x0 dx. Okay, this is the formula for, the generic formula is the one I wrote before, is the psi star of x, phi of x dx. Psi is x1, phi x0. And what is this? Well, this is delta of x1 minus x0. So it is 0 if x1 is different from x0. Unfortunately, instead of being 1, which would be the case for a normalized basis, it's infinity if x1 is equal to x0. So again, there is a little bit of a difference from our basis, but at least this is the case, right? That if these two vectors are different, the scalar product, these two objects are different, the scalar product is 0. If they are equal, okay, it's infinity. We have to deal with that. As a consequence of this, there is a completeness relation with these objects. That is that the integral of this thing is actually the identity on the space. And frequently, people use a strange notation, but again, it's perfectly justified. They write that this is equal to x psi. Okay, remember that before, again, a finite dimension, we had phi is equal to sum over n equal 1 to d, and then, okay, I write it like this, phi n, a basis, phi n psi, these are the coefficients. So again, here we can, therefore, write the wave function as formally the scalar product between psi, the state, and a delta function. Okay, so this notation is justified. Okay, I need to make two remarks now. One is in the lecture notes, the other one is also in the lecture notes, but much later. So the first remark I have to make is about units. So let me check something about units. So if x is position, right? I can erase also this. If x is equal to position, its units is meters. Right? Now, let's see what are the units in this expression. I will erase it, sorry, I should have written here. This is a vector, so this is unitless. The unit is a number. Now, here what do we have? Well, we have here meters. So these two things must be together 1 over meters. And now, how do you do the distribution of these two? Well, remember I told you before that we have a normalization condition, integral dx psi of x square is equal to 1. Well, so then this means that if this is meters, this is 1 over meters. Meters minus 1. Then this with a square. Therefore, the wave function itself is square root of meters. And therefore, again, our vector that is not a vector has also a dimension. Sorry, square root of meters minus 1 is also square root of meters minus 1. And now you can play around with that and you can verify that indeed this delta function has the right unit. So here, let's do the units here. We said that this is square root of meters minus 1. This is square root of meters minus 1. This is meters. Therefore, this is 1 over meters. And the delta function has the property of being that the unit is 1 over the unit of the object that is inside. Okay, so everything goes well. But if you want, you can take this one as another evidence that this object is not a proper vector. Now, the other remark I want to make, some of you have asked it before, is the following, is that this Hilbert space, L2 of R, has a countable, has countable bases. So countable means that there exist bases that can be written as phi 1, phi 2, phi 3, and so on. It's just that instead of stopping at phi d, okay, that would be the basis for a finite dimensional system, it never stops. And it continues. There are infinitely many, but it's countable in the sense that they're indexed by the natural numbers, 1, 2, 3, 4, 5, and so on. And these are proper bases. So proper vectors. These guys, of course, there are infinitely many of them and continuously many. You cannot count them, right? It's like the continuity of the reals. But they are not a proper basis. So when we speak of infinite dimension in quantum mechanics, we refer to a vector space that has, of course, infinite dimensions, but infinitely countable dimensions. The fact that some operators have a spectrum that is continuous, like the reals, does not mean that you cannot describe all these vectors in those bases. Now you say, well, what is an example of that? Can you be a bit more concrete? Well, we will see the most famous example of these things when we study the harmonic oscillator. So bear with me, this will be at the end of the chapter on dynamics, but an example of these, an example would be the eigenstates of the harmonic oscillator. reference at the end of this chapter. Very well. So now I said everything I wanted to say about description of the systems. We have seen that vectors are described in a very similar way as what is done for finite dimensions. It's just there are functions instead of coefficients. And we have discussed a little bit that one has to be moderately careful with these objects. Now let's study the operators. For the degrees of freedom for a material point are position and momentum. Every other degree of freedom can be derived from them. The energy will be a function of position and momentum. So let's describe the position and momentum operators. Well, I will write them down first like this, the position operator, x, integral. So this is operator. Huh? This is a number. So again, barring the fact that these guys are not proper vector, this looks very much like what we had with discrete variables, which was that some physical quantity A is sum over n eigenvalues, eigenvectors. Right, so that's same structure here. For the momentum operator, of course, we have something very similar. P, pp, dp. Right? And all that I said for position vectors also holds for momentum vectors. These objects are also not proper vectors, and so on and so forth. Later we'll find what is their wave function. Now, very important point now for your formation. This is one of the things that even if you forget quantum mechanics, you need to keep in mind. At this point, it's not because I've written x and p that these guys are position and momentum of the same material point. I've written x and p, but this could be the position of one material point, and this could be the position of another material point, that because I wanted to, I write p. So I need to give a relation between x and p. So why I think this remark is important, it's idiotic, but it's important, because sometimes we give a metaphysical status to objects because we use some letter. It's written P, therefore it must be momentum. No, it's written P, can be anything. What defines whether it's position and momentum? How it transforms under the Galilei group. Now, I'm not going to do group theory. I'm just going to state the result. Okay? So conjugate variables, what would be conjugate variables in a Hamiltonian, classical Hamiltonian theories are, you can study how they transform and you find that the criterion for conjugation is the following. So these are position and momentum, if and only if x and p do not commute, not only do not commute, but they do not commute according to this rule. Now, well, this rule is actually pretty dramatic, right? Let's see what it implies. Well, the h bar is a unit factor. So, it's a number that the theory cannot predict. You have to measure it. You have to try to find out what this number is. It turns out that it's the famous Planck constant divided by 2 pi. But what really is dramatic is this. So up to this complex number and this unit thing, the commutator is the identity. It means for every state, x and p do not commute. Right? Okay, this gives rise to the famous uncertainty relations, delta x, delta p is equal to h bar over 2. Sorry, larger equal than h bar over 2. And so there are two consequences of this. One is a warning that I made some time ago. You can look at the trace of the commutator x and p. You have a tutorial that says that if x and p are well-behaved operators, especially finite dimensional, the trace of a commutator is always 0, right? Because the trace of xp should be equal to the trace of px. Okay, however, when the trace of xp is infinity and the trace of px is infinity, these two infinities need not to be equal. And in fact, if you look at the trace of this fellow, is IH bar times the trace of the identity, and we are tracing the identity of an infinite dimensional Hilbert space. So this is infinity, certainly different from 0. It's one of these strange things that can happen in infinite dimensions, right? Again, the argument is that if trace of xp is infinity and trace of px is infinity, this does not necessarily imply, and in fact it does not imply in this case, that trace of xp is equal to trace of px. Whereas, of course, if these two numbers are finite numbers, then trivially the two are equal. And the second remark is that indeed, because it's the identity, there is no state, there exists no state such that psi xp psi is equal to 0. Which means in no state it can happen that both position and momentum are sharply defined. In fact, technically in no state it can happen that either position and momentum are sharply defined, because if delta x is equal to 0, well, it will be very hard to get these different from 0 unless delta p becomes infinity in the suit. Again, you know, when you go to infinities, you have to be very careful because it depends how fast it goes to infinity. So you need to take a sequence. You take your delta x that goes to 0 and your delta p that goes to infinity, and in such a way that the product of the two remain always bounded by these. And we said before, there is no state such that x is equal to x0 sharp. That delta function is not a proper state. So strictly speaking, you will never have delta x equal to 0, but you can have it as small as you want. The price to pay is that delta p will become very large, and vice versa. Okay. Now, well, I've given these operators. How do they act on the wave function? Well, let's start from here. It's pretty clear what's going to happen. So what is the action of x on psi? Well, let's try. X int x dx that acts on, well, I have to use a different letter. Let me use y. It's the same x as before, just a change of, sorry, not y. We had psi of y dy. And now, if you look what there is, I mean, there is a vector here, a line vector, a column vector, the rest are numbers. So we get x, I can rearrange things. Now I have x scalar products xy, dx, dy, but we saw before that this is delta of x minus y, and therefore this becomes integral of x psi x xx x dx. So what do we see here is that if I take the wave function psi and I apply the operator x, I get another vector described by another function, f of x is equal to x psi of x. So the new function is a function such that x multiplying, that you take the new function is such that is obtained by the previous function by multiplying that function by x. Here you may start seeing that the class of square integrable functions, you must be a bit careful with them. Because you would also like this guy to be a proper vector. So not only you want psi of x to a square integral, you also want x to psi of x to be integral, and maybe x squared to psi of x to be integral. So the decay should be quite fast. I will not go into more details. All the examples we are going to find in practice will satisfy all these properties, so don't worry about strange cases. So this is the action. This is the action of the operator x on the vector psi. Okay? Now, we can iterate that, by the way. So maybe I will do it just here. If I were to take any power of the operator x, well, it just gives me the power n here, the power n here, and the power n here. And so the function of n would be a... So you see the position operator is not particularly difficult to deal with. It's just multiply your function by x. Your wave function by x. Okay. So what do we see from here? Right? We see that the average value of x to the power n on the state psi is simply equal to integral x to the power n psi of x square dx. But if you don't do quantum mechanics, if I just tell you there is a distribution of positions, rho of x, so distribution of position, can be classical, this one, rho of x, and I ask you what is the average of x to the power n, well, you would write certainly these. Huh? So, by identification, we find that the square of the wave function is the distribution of position. Well, it's similar to what we had. So and of course it's a probability distribution, right? It's not a probability proper with discrete values. It's a probability distribution like the ones you might have seen in other modules. How do you use a probability distribution? Well, typical question of final exam for those who are listening. What is the probability of finding the material point, or let's call it the particle, between x equal a and x equal b? Okay, this would be the integral between a and b of the probability density. Okay. Now, I told you all that I wanted to tell you for the position operator. Now let's look at momentum. Now, so what is this? There are various ways of answering these. We were going to do first the simplest one, or the most direct one, which is the position representation. So, you see, if I were just to plug this expression into the previous one, I would get something like integral p psi of y, or well, psi of x, whatever, psi of y, and then I would have p py dp dy. And now, what is that thing? We don't know yet. We are going to find it out. So I will leave this for a while, and I will take a different route. We are going to work with wave functions in position representation, and to see how this operation p behaves. So to do that, where do we start from? Well, commutation relation, right? xp is equal to IH bar 1. Now, I will show you something, how you can get two operators that have identity as commutation relation, and then you will have to trust me that this is the unique solution, at least for differentiable functions. So look at this. Relax, that's easy. What is the derivative of the function x times f of x? Well, we all know how to do this, right? It would be, the first one you derive these, we are left with f of x, and then plus, you take x and you take the derivative of these. Okay? But now, let me rearrange these in a different way. D over dx, x, f of x, minus this guy, x, d over dx, f of x, is equal to f of x. Now, let me write something slightly different. Have a, b, f, minus b, a, f is equal to f. So you can see position operator and something, a, again the same a, position operator, for every f. What do you conclude from these? Well, you would conclude that a and b, sorry, do not commute, so let me do it calmly. Sorry. You would conclude that AB minus BA is equal to the identity. Right? AB minus BA doesn't change the vector. Okay, but that's essentially what we want, right? Up to a IH bar somewhere there, that's exactly what we wanted. And since this is position, that thing is more or less momentum up to correcting for this factor, and we find that the representative of momentum, P on psi, would be equal to integral minus IH bar d over dx acting on psi of x, x dx. This is the action of the momentum operator in position representation. Sometimes in the textbooks you find everything written without the vectors. You find something like this. It's good for memorizing. I find it maximally confusing just having like this, because you see that there are some other objects here. So there is a vector here, there is a pseudo vector here, there is a wave function that is not mentioned. But I mean, this is good to memorize, just to keep in mind. Very well, so now we have the momentum operator. And, well, we can take we can take the moment of the representation. However, okay, here is something that worth mentioning. If you want to compute the moments of the momentum distribution, the average p to the n on psi in the position representation, well, this is a bit messy, right? Because this would be something like, okay, there is a minus IH bar to the power n that we don't care too much. Integral, now careful, there is a psi of x here, psi star of x, minus IH bar d over dx to the power n. Sorry, I've already taken out that thing before. So this is dn over dxn psi of x dx. And this is not something that you cannot express these as some operation on rho of x that was psi of x squared. So this tells you, I will not go too much into these details, that you need more than the information about the position distribution in order to compute momentum. It's normal because they do not commute, right? So you cannot, if you were able to compute momentum only from the position distribution, essentially by knowing the position distribution, you would know everything there is to know about momentum, which would be very strange since these operators do not commute. Okay, so now let's try to find what are these guys. Those guys. The object that look like the eigenstates of momentum. Okay, well, what is it? What is the wave function? Well, I want a wave function such that minus I h bar d over dx wave function of given momentum, let's say p0 of x, is equal to p0 psi of p0 of x. This would be the wave function, so I'm looking for the vector p0 whose wave function is like that. Okay? So what is the solution to this eigenvalue equation? Well, it's pretty clear what it is. For every p0, which is well defined, this would give me psi of p0 of x is something like, well, an object e to the I p0x over h bar. That's our exponential solution. Now what is c? Well, you say, well, we have to normalize it, but we can't. Integral psi of p0 of x square dx. What is d square? Well, this is c minus infinity infinity. This would be c square integral from minus infinity of 1. Square of this is 1. So this is infinity. Again, not surprising, right? We have another type of function. Before we had the delta function for position. Now we have the exponential, complex exponential for momentum. Another one that cannot be normalized. Well, it's not entirely surprising, right? That you get these. However, there is a nice choice for this constant. Usually the choice that is made is this. It's a strange number. It's 1 over square root of 2 pi times h bar, right? And the reason to choose this, I can let you verify it as an exercise, is that if I choose this one, I will get that P0, P1 is equal to delta of P0 minus P1. If I don't choose this one, I would get a constant in front. So with this choice, this is correct. There's another way of writing this thing, which is like that. So sometimes this EI P0x over h bar is written as, how does that go? E to the 2 pi I x over the de Broglie wavelength. This is the famous de Broglie wavelength that is given by, let's see, sorry, this 2 is wrong probably. I would have to check that. Anyway, the de Broglie wavelength is usually given by, no, it's correct, sorry. H bar over, so 2, if you identify these coefficients, you find 2 pi h bar over mv, which is equal to h Planck constants over mv. This is called the de Broglie wavelength, and you have a tutorial where you're asked to estimate these for an atom, for a human being, and for other objects of interest. Very good. The last point I need to make before we finish this part and we move on to the dynamics is what is called the momentum representation. So, you see, the construction we have made so far, it's almost complete. Maybe I should summarize this in a way that is not done exactly in the lecture notes, but, and you will see a pattern emerging that, so okay, let's start from here. Okay, erase this one. And now we have this operator, right? We know that the wave function associated to x0 would be the delta x minus x0. And we know that the wave function associated to p0 is going to be 1 over square root of 2 pi h bar e to the I p h0 over, sorry, not equal, this is the wave function associated to it. But now, and then we know that the action of this operator would be minus I h bar d over dx. Now you see that there is a kind of asymmetry here. We have two things, position and momentum, but we discuss them all as a function of position. We say, well, why? We could have just as well discussed everything as a function of momentum. Then what would you get? Well, it's not too, you don't need too much of imagination to see what's going to happen there. So we could have defined a wave function. So here the wave function is psi is equal to integral psi of x dx. But we could have defined the state is a change of basis, integral psi tilde of p dp. It's really a change of basis, huh? Careful. This vector and that vector are the same. I can look at it in the basis of position or in the basis of momentum. Now what would I get? Well, I don't think it takes a genius to understand that in this case the wave function set to p0 would be delta p minus p0, and that the wave function set to position would be something like that, same coefficient, but with a minus sign. The minus signs come from the commutator relation. So it would be e to the minus I x0p over h bar. And what does the position operator look like in that representation? Obviously, it's going to look like this, but again with a minus sign because of the commutator. So it would be I h bar d over dp in this representation. Okay? And now let's see what the relation finally, what is the relation between these two? Between psi of x and psi tilde of p. It's the same vector. It's a change of basis. There must be some relation, right? That cannot be completely uncorrelated. Well, let's try. The same vector psi is equal to integral on psi tilde of p dp, and now here I insert the identity. You say, well, it doesn't change much, right? Indeed, it doesn't change much, but now let me write the identity as integral dx x. Let's remove this parenthesis, it's a bit bothersome, right? Now, what do we have here? Well, there's xp here. But xp, if you refer to the wave function, so this is the projection of the p in the basis x. So it's written here what it is 1 over 2 pi h bar e I px over h bar. And now I can, this you have to trust me that with all these square integrable functions, things, the integrations can be exchanged. So I can exchange this one and that one. And I will get, let me try to play with the colors. Let's see if I succeed. Sometimes I don't. Integral dx x. And then I have a strange thing in there, which is 1 over square root of 2 ph bar psi tilde of p e to the I px over h bar. And of course, I have forgotten integral dp and p. No, p has disappeared. But look at this and at that. What is this? Well, this is psi of x. So this is the relation between psi of x and psi tilde of p. You may recognize these up to some h bars that hang around for some reason. You may recognize this as a Fourier transform, right? The Fourier transform between x and p. And of course, the opposite is the case. I mean, you can invert this equation, and you can find that psi tilde of p is the kind of same Fourier transform, but in the other direction. Integral psi of x e to the minus I px over h bar dx. So with these two formulas, you can switch around between the position representation and the momentum representation of the same state. Is a change of basis. There's nothing happening there apart from, just changing basis. Very last remark before we finish this. You may ask the question, if I know everything about position and everything about momentum, do I know everything? The answer is no. Let me clarify this statement in a proper way. So the question I'm asking is this. Okay, this guy is the state. So I know everything I can know, right? All properties. So far, so good. This guy is equivalent to give the wave function. So far, so good. He's also equivalent to give the wave function in momentum. So far, so good. So these three pieces of information are the same, and they identify the state. Now you may say, well, I have measured position. So I have the information about rho of x. Or alternatively, I have all the x to the n for all n. I have the distribution of position. The distribution uniquely identifies the momenta uniquely identify the distribution. And I also use this guy. So I have the distribution in momentum. So in other words, psi tilde of p squared. And in other words, I have all the pn. Are these two pieces of information enough to reconstruct the state? The answer is no. To reconstruct the state, you need everything. You need all the distribution. So exact reconstruction of the state requires all the cos theta x plus sin theta p, sorry, small mistake, to the power n average on psi for all theta. Now you may say, well, what is this observable here? It's a bit strange observable. By the way, the units don't work very well. I should put some units there. Forget about the units. Well, it is one of these observables that is not easy to explain in, in narrative terms, what it means. We don't have an easy English expression for that, but it's a linear combination of these two operators, and you need all of them. So the analog of these, right, if you remember, and with this I finished this lesson, remember that for a qubit, a two-level system, the state is equivalent to the block vector, and the block vector is the average value of sigma x, sigma y, and sigma z. So for a qubit, if you measure three things, you get these three average values, you reconstruct the state. For continuous variable, material point, it's not enough to measure two things, position and momentum, to reconstruct the states. You would have to measure all these things. Okay, with this we finish the lesson about the description of a continuous variable system, of a material point. And the next lesson we will start with the Hamiltonian and the dynamics. I have to send a message to my technician saying that we stopped the recording, but you can stop watching.